Till now we have concentrated our discussion on the fabrication of the materials and different kinds of structures. Say if you recollect, we can say that first we have started with bulk crystal growth. Then we have concentrated our discussion on epitaxial growth of different materials. Okay, so, mostly we have concentrated on these two aspects, one is bulk, another is the epitaxial crystal growth. Now, after the growth is over, or say in some cases we have even grown the p-n junction as a test case. So, in all such cases we need to characterize our sample, because how do you know the properties of the grown epitaxial layers or the bulk crystal unless we characterize it. Since this is an electronic material class, so we should concentrate our discussion on the electrical characterizations of material, okay, because these all materials are used for electronic applications. So, that is the reason no mechanical testing or thermal testing is required for our material, because these are not the material to be used for any mechanical purpose, okay, unlike in ceramics or polymers. Therefore, we shall concentrate our discussion on the electrical characterization of materials. Okay. Now, so far as the electrical characterization of materials is concerned, there are two ways using which we can characterize it. One is by the method of 4-point probe, another by Van der Pau technique. Van der Pau technique. Now, using any of the techniques, basically we can characterize the resistivity of the material, right, that you have performed in your lab class also, the resistivity of the materials. Now, once you know the resistivity of the materials, then the other properties of the material, namely the carrier concentration or the mobility of the material, can be calculated. So, what are the aspects that we would like to characterize? One is the resistivity, number 2 is the carrier concentration, number 3 is the mobility, number 4 is the type of conductivity. Type of conductivity means whether it is N type or P type. Okay, so, these are the 4 basic characterizations that we follow after making a material, or once the material is grown, then these are the properties that we would like to study of a particular material. Resistivity, and you know that resistivity and conductivity is the same thing, only that 1 by resistivity is the conductivity. So, as discussed earlier, that this electrical characterization, either we follow the 4-point probe or we follow the Van der Pau technique. Now, what is the difference between these two techniques? What is the difference between these two techniques? Is there any difference? When we shall use 4-point, when we shall use the Van der Pau technique? The main difference between these two techniques is the contact. in 4-point probe we need not to make any metal contact on the sample. It is basically contact by pressing, it is basically contact by pressing. Okay. As the name implies 4 point, that means there are 4 platinum or gold needle like contact which is pressed on the surface of the sample, right. So, it is basically a press contact, and I shall show you the attachments using which you can contact by means of pressure, just a small pressure because it is connected with some spring attachment. So, it can adjust itself. Okay. But for Van der Pau technique you must have ohmic contact on your samples, and when we talk about the ohmic contact, it means first you take the sample, you clean it, then you make 4 metal contacts on it, 4 metal dots. Suppose this is your sample, you make 4 metal dots of say 1 millimeter diameter, and these metal dots are thermally evaporated on the surface of the material to be characterized. So, if you want to characterize say this material, say this is your material, if you want to characterize it, first make some 4 gold dots like this. Okay. Then you connect copper wires etc., and use the formula for the measurements of the resistivity using Van der Pau technique. So, ohmic contact is required. So, when we talk about ohmic contact, there must be some other contact, then otherwise why we are telling that it is ohmic contact. That means there may be non-ohmic contact as well. There is no guarantee that a metal and a semiconductor will provide you all the time ohmic contact, not necessary. The contact can be ohmic, it can be non-ohmic in nature also, depending on the work function of the metal and the semiconductor, that we shall discuss in a separate lecture. So, that is very important thing, when the contact will be ohmic, when the contact will be non-ohmic. Generally by non-ohmic contact we understand it is a Schottky contact, it is a Schottky contact. So, that means for ohmic contact the current voltage characteristics will follow this kind of a variation. That means it is perfectly linear on both sides of the origin. When the positive voltage is applied, positive current will be available. When negative voltage will be applied, negative current will be available with the same amount of current, okay? Same proportion, same amount of current we shall get on both the directions. So, then we can say that it is a ohmic contact. So, this is the characteristic of ohmic contact, and if it is not a ohmic contact, then the characteristics will follow such kind of a curve, which is known as the Schottky contact or the rectifying contact or the rectifying contact. This is IV characteristics. Okay. And in the reverse bias, small amount of reverse current will be made available. Okay. So, these are the two contacts, this is ohmic contact, this is non-ohmic contact, it is known as basically Schottky or rectifying contacts. Why it is known as rectifying contact? Because you see that this IV characteristics of a metal semiconductor assumes the form of a rectifier diode, because that is the characteristics of a rectifier p-n junction diode. In forward bias, it will allow current to flow, but in the reverse bias it will not allow the current to flow. So, the current will be unidirection, current will be available in unidirectional direction only. That means, in the forward bias only the current will be available. Okay. That is the rectification property. This phenomena is known as the rectification. Using this property, AC is converted to DC. Okay. So, this Van der Pau technique, for this Van der Pau technique you need ohmic contact. For 4-point probe you need not to make any ohmic contact. So, that is very important thing. Another important aspect of these two contact is that, as we shall discuss, you will find for 4-point probe your sample is regular in nature, the shape must be regular in nature. Okay. That means, better if you can use a very thin slice of large diameter material. Why, that we shall discuss in detail. But in Van der Pau technique, such kind of specific shape of the material is not required. So, these are the main two differences between the 4-point probe and the Van der Pau technique. Remember that using your 4-point or Van der Pau technique only we shall be able to measure the resistivity of the material, not any other thing. The rest of the properties or the parameters can be evaluated by Hall effect measurements, not by Van der Pau or by 4-point probe. But for Hall effect measurements you need the Van der Pau configuration. That means, if you want to make some measurements using Hall effect, then you have to take the sample, you have to make ohmic contact in it, what you have done in case of Van der Pau technique, and then you have to measure. So, that is why we say that for Hall effect measurements we always follow the Van der Pau configuration, not the 4-point probe configuration. Okay. So, these are the differences. Now, for 4-point probe, you see that this is the sample of diameter d and the thickness is w. Okay. Then you see that 4 probes are there. This is the needle like probes 1, 2, 3 and 4. Here I have shown like an arrow. So, this is basically a needle type of material made of either platinum or gold, and it is placed on the surface of the material. You see that between the two outermost probes, this is one outermost probe and this is another outermost probe. Between these two outermost probe, a current is applied from the constant current source, and the corresponding voltage is measured between the two inner probes. The potential difference between the two inner probes were measured using a voltmeter, and the current is supplied between say 1 and 4. If I consider it as like this, say this is 1, this is 2, this is 3 and this is 4. These are the 4 probes. So, current is between this 1 and 4 and voltage is between this 1 and 2. This is the configuration for the measurement of the 4-point probe. Under such a situation, what will happen, that we can calculate. There may be two cases, one may be the bulk case. Another is the epitaxial layers, because in semiconducting or electronic materials these two cases are possible. One is the bulk, another is the very thin grown layer which is known as the epitaxial layer. In that case we can consider that it is a sheet of material, because very small thickness of the epitaxial layer we consider. So, we can consider that that is a sheet. So, one is the bulk, another is the thin film or the sheet or the epitaxial, whatever be the case, that is known as the thin sheet say. So, these are the two cases which we can measure. Now, if the bulk is considered, let us first take the case of the bulk, then the differential resistance it is given by delta r rho into dx by A. What is this? This is r equal to rho into L by A. Since I am measuring the differential resistance, that means this L, the length which we are considering, is basically x plus delta x, between x and x plus dx. So, very small region we are considering, because that is your differential resistance. That is why I have put delta r also. So, if you take this kind of a configuration and if you say that this is say x 2, this is x 2, this is x 1 and the probe spacing is S. The probe spacing is x, S is probe spacing, and x 1 and x 2 are the distances of the inner two probes from a particular coordinate axis. Now, under this situation I can make r equals to integration of rho into dx by what is the area. Here you see that for a bulk material, we are considering the bulk material. For a bulk material, the current, that means in 1 and 4, we can consider that the current is, we will assume a spherical shape, because from the if you consider a point inside the bulk material, and if you think that from that point towards the surface, what should be the path of the current? It will assume a spherical type of path, as if the current is emanating, it is pushing through from the inner to the outer surface. So, under such a circumstance, the area will be twice pi x into x, that means twice pi x square. Why? Because you can consider that what is 2 pi x? 2 pi x is the perimeter, 2 pi x is the perimeter, and if this x is very small, then we can consider that that perimeter is the length and that is the breadth. So, the area is 2 pi x multiplied by x for this case. And what should be the limit? The limit is say from x 1 to x 2, that we have assumed. So, you can write that this is equal to rho by twice pi x 1 x 2 dx by x square. Then if you work out this integration, what you will get, or r will be equals to rho by twice pi minus 2 by x, x 1 x 2. Okay. This is equals to how much? No, not 2 by x, it is 1 by x. 1 by x. Okay. So, under this circumstance, it is, if you put the value, you will find that it is 1 by Yes, that means this x 2 minus x 1 is basically the probe spacing. What is x 2 minus x 1? It is the probe spacing between the two probes, the space between the two probes, and we have assumed it as S. We have assumed it as S. That means, we have considered that it is a uniform probe spacing. There are 4 probes 1, 2, 3 and 4, and each having distance S, the spacing. So, this is equals to 1 by 2 s into rho by twice pi. Okay. Now, what is R? Hmm?
How it would be s, because 1 by x1 minus 1 by x2. So the difference is x2 minus x1, that is s, but divided by x1 into x2.
Divided by
x1 into x2.
that would be equals to rho by twice pi
1 by x1
minus
1 by x1
minus
x2 1 by x2
yes
plus 1 by x1.
yes
Then rho upon 2 it comes out to be x2 minus s upon x1 minus x2 x1 minus x2 divided by x1 into x2. x2 minus x1 I have thought. So x1 minus
this
x2
thing
is s
x2 minus x1 by x1 x2.
But in numerator x2 minus x1
x2 minus x1.
by x 1 s 2, that is equals to rho
by 2 pi
twice pi
x1 into x2 is by x1 into x2.
x 1 into x 2. Then what is the value of x 1 into x 2? What is the value of x 1 into x 2? What is the value of x 1 into x 2? What is x here? Yes. Suppose this is your 0. Suppose this is your coordinate axis 0. Yes, then it is a square. Suppose I consider this as the x equals to 0, then yes, that is equals to rho by twice pi s by 2 s square. So, that means equals to 1 by twice s into rho by twice pi. Some approximation is there obviously, right?
So could you just give the reason once again for that?
Which one?
Area.
Yes, area is basically, here you see that we are considering the bulk. So, when you consider a bulk material, you can assume that the current is coming out from the inner to the outer side. Why? Because basically the current flows, the contact is on the surface. It is a bulk material, the contact is on the surface. So, when current is coming out from this point to that point, it is coming out through the bulk. So, that means as if the current is thrusting or pushing outward, okay, that is a projection from the surface. So, it will like a surface, a sphere. So, now in that sphere, if you take the area, so what is the area? Because we are considering the area A, the area is basically the circumference is twice pi r, right, and if this r is very small, if this r is very small, then you can consider that the 2 pi r is the circumference which will act like a rectangle with 2 pi r as the length and r is the breadth. So, it is 2 pi r into r. That is possible if you consider, if you take the projection of that thing for a very small area. Okay. No, no, here we are considering, see, we are considering the resistance is uniform. Okay. We are considering it is a uniform. Here there is no variation of resistance is possible, because the grown material is a uniform material. You are not measure using this technique, you cannot measure the resistivity of wood or bricks. It is for the well synthesized semiconducting material. Okay. Now, you can think that area in other way also. He has some suggestion. What is your suggestion?
About area 2 by x into.
Yes.
That's Q.
Okay. We can discuss in later also. So, now this is the resistance R, and this R equals to how much? V by why I? It is I or anything? No, I is there, but whether it is I or 2I or 3I or 0I?
2 I. Hole and electron.
No, it is 2I, because it is basically the superposition of current. It is basically the superposition of current, because
Two times we are calculating. We are applying current here and measure the voltage across here, and we apply current.
no, it is because you see that between these two probes, when we measure the current is total current we are measuring, it is equals to 2I. It is not only I, because two probes are there. If it was a total two probes material characterization, you are measuring, you are sending the current between two and measuring the voltage, then it is V by I. Since we are introducing 4 probes, so basically that is a superposition of current between the outer two probes, and it is 2I. So, this R equals to V by twice I, or rho equals to, you see what is the value, rho equals to twice pi by twice pi into S into V by I. That is the solution for this 4-point probe bulk material, not the thin film or thin sheet material. It is rho into twice pi S V by I, where S is the uniform spacing between the any two probes. Now, if we consider the thin sheet, for thin sheet we can start from this equation. For thin sheet we can start from this equation, only difference is that here the current will be the circular ring type of thing, because it is a thin sheet, it is not coming from inside the bulk. Okay. So, that means here it will be twice pi x into T, if T is the thickness of the material. If T is the thickness, let me write down for thin sheet. For a thin layer, thickness T very less than S, we get current rings instead of hair. Area equals to, then area equals to twice pi x into T, T is the thickness of the thin layer, and the derivation will be r equals to x1 to x2 rho dx twice pi x into t, that is equals to, if you consider this thing, you will find that it is equals to rho by twice pi t into ln 2 equals to ln 2, because 1 by x is ln and it is ln by 2. So, again here you see that r equals to v by twice I as usual. This is equals to rho into twice pi t into ln 2 or rho equals to pi t by ln 2 v by I. And in this relation, the important aspect is that it is independent of the probe spacing. Earlier it was a function of s. Earlier we have seen that rho was twice pi s v by I. Here you see that there is no s or the probe spacing, only the thickness t is important here in this case. Okay, and this is equals to pi ln 2 t v by I.
Thickness is independent of x.
Which thickness?
T.
T is the material property. T is the material property which you are going to characterize. Suppose yes, T is the thickness of the, yes, if it is a epitaxial layer, then T is the thickness of the epitaxial layer. Suppose you have grown silicon epitaxial layer on silicon substrate. Your silicon substrate is say 400 micron. Your silicon substrate is say 400 micron. Is 400 micron, and epitaxial layer on it is say 0.1 micron, then T is 0.1 micron. Remember that in such case the substrate used is taken as very high resistive, otherwise the contribution of the substrate will be there in your measurement. For 3-5 semiconductors, generally we grow the epitaxial layer on semi insulating substrate that is available. For semi insulating means you are growing that 0.1 micron layer on an insulating base. So, that means the contribution of the substrate is not there in the epitaxial layer electrical resistivity, right. Suppose this is your substrate, this substrate is 400 micron and this is your layer of 0.1 micron or 1 micron. So, that means you have grown this layer on this substrate, then using a 4-point probe you are measuring the characteristics of this layer only, not this thing. Okay. So, now how you will decouple it? Decouple you can make in such a way that you can grow this layer on a very high resistive substrate. So, that what you are telling that the current will follow the least resistance path and it will not take the bulk, only the surface property will be available. Otherwise, you can use a semi insulating substrate on which you can grow the epitaxial layer. In that case, there is no scope of the current to flow through the substrate, because you have been using the semi insulating. So, all the current will be passed through that epitaxial layer. Otherwise, you can use sapphire substrate. You know sapphire is a non-conducting substrate, Al2O3. So, you can take a sapphire substrate, a glass substrate, glass is also non-conducting in nature. So, you can use those substrate for the growth of the epitaxial layer for electrical characterization. Otherwise, how you will calculate the mobility or the carrier concentration? How you will ensure that the carrier concentration or mobility is not coming from the substrate. Okay. So, semi insulating means it is very high resistive. Say the resistivity is 10 to the power 7, 10 to the power 6 ohm centimeter, very high, not a characteristics of the semiconductor. In semiconductor, what is the resistivity? 0.001 to 1 to or up to say 10 ohm centimeter. Here it is 10 to the power 6, 10 to the power 7 ohm centimeter. That means the resistivity is very high. So, you cannot consider it as a normal semiconductor. That is why it is known as a semi insulating substrate. Okay. So, in this case you see that for the thin sheet, it is independent of the pressing S, and only it depends on the thickness of the material. Now, this thickness of the material, in some books or in our lab we have mentioned that there must be a correction factor, probably you can remember that thing. Here you see that this expression rho equals to T into V by I into pi by ln 2, that is equals to the thickness multiplied by the ratio of voltage to current multiplied by the correction factor Cf. This is the correction factor pi by ln 2, and it can be different also for different material. Remember that in this particular case we have considered that the current rings will be there, or it is an uniform thickness, but in actual practice there may be some difference with the ideal sample situation. The sample may be rectangular in nature, may not be circular in nature, the thickness may be different. That means from plus x to minus x direction there may be some variation of the thickness, that is possible. So, under such a circumstance you have to use the correction factor. Generally in such a case the correction factor is taken as 4.53. Why? It is the value of pi by ln 2. It is the value of pi by ln 2. Pi by ln 2 is 4.53. Right. Now, another important thing is that since we are considering a thin sheet or an epitaxial layer, so what is the sheet resistivity? Sheet resistivity Rs is equals to rho by T. Sheet resistivity Rs equals to rho by T, or this is equals to V by I into correction factor Cf. Then we should write it is sheet resistance, not resistivity. Why? Because rho is the resistivity and we are dividing the resistivity with thickness. So, that means it becomes resistance, ohm centimeter by centimeter. So, it becomes ohm. So, it is sheet resistance. Now, why the sheet resistance we have calculated? Because it is a thin sheet. So, we can characterize that thin sheet with sheet resistance or the sheet carrier density. In later stage we shall find that we have measured the for thin sheet we have measured the sheet carrier density, That means the density of carriers in that particular sheet of material or in that thin film of material, right. So, this is the 4 probe method. Now, if we consider the another point I should mention that here you see that the correction factor is pi by ln 2 and we have considered that uh, it is a uniform circular material or the sample having thickness t. But if it is other type of sample of say irregular shape, it can be rectangle, it can be triangular shape, any kind of shape is possible, then this correction factor will be different. And this correction factor is available, you can write down the site from where you can take the correction factor. It is provided by Bridge Technology, BRIDGE, Bridge Technology, USA, through haldor.html. If you visit this site, you will find that they have listed the correction factors for all types of samples. They have listed the correction factor for all types of samples, they have provided the graphs for different kinds of samples. So, depending on your actual sample shape and geometry, you can choose the proper correction factor, because correction factor is very important. In most of the cases, you will find that our sample is not uniform. Then this theoretical correction factor which we have used pi by ln 2 is not valid. Then you can visit this site, you can check what should be the correction factor for your case and you can put the proper correction factor instead of 4.53, right. So, this is all about the 4-point probe. So, in a nutshell, 4-point probe you do not need any metallic contact or ohmic contact, only you have to measure the current between only you have to pass some current between two outermost probes and you have to record the voltage between the two innermost probes and you must know the thickness of the sample, that is all. And if it is uniform in nature, that means if your diameter of the sample is very greater than the probe spacing, if your diameter of the sample is very greater than the probe spacing, then you can consider that the correction factor as 4.53. It is valid generally for D greater than S, D greater than S, diameter is greater than the probe spacing, then you can consider that it is 4.53. But the diameter is basically the characteristics of a circular sample or a sample having circular shape, because all the wafers are available in circular form, that is why we are discussing as a circular shaped sample. But in your laboratory when you grow a sample, it can be rectangle, it can be anything. So, depending on that you have to change the correction factor which is available from this site. Now, the next part of our discussion is the Van der Pau technique. First thing is that make ohmic contacts. Which was not required for your Okay, make ohmic contacts. Number 2 is that you can use arbitrary shape. Thin plate sample containing 4 very small ohmic contacts placed on the periphery. Preferably in the corners. I can show you the configuration. Yes, this is the configuration of the ohmic contact for Van der Pau configuration. See, this is, if this is a circular sample, these are the contacts. So, that is preferred. In the corner, it is acceptable for square or rectangle, but for square or rectangle contacts at the edges or inside the perimeter, because it is inside the perimeter or it is at the edges, it is not recommended. It is to minimize the current path and to minimize the contact resistance, that this kind of circular shaped or this kind of square or rectangle shaped sample is acceptable. These are the dots are the ohmic contact through which the current or voltage will be measured. You see that this is 1, this is 2, this is 3 and this is 4, that is in the counterclockwise or anticlockwise direction we have put the numbers 1, 2, 3 and 4. That means, it can be arbitrarily shaped thin plate sample. Thin plate means thin samples, epitaxial samples containing 4 very small ohmic contacts placed on the periphery or in the corner, preferably on the corner. And if this is the situation, then Van der Pau configuration, you can measure the resistivity by using the Van der Pau equation. It is known as exponential minus pi R A by R S plus exponential minus pi R B by R S equals to 1. So, this is the Van der Pau equation. This is Van der Pau equation. So, originally the Van der Pau proposed such equation to measure the resistivity of a sample using that kind of a configuration. Now, you see that R S is the seat resistance, R S is the seat resistance which we would like to measure. And R A and R B are the two characteristics resistance which we would like to measure using our Van der Pau configuration. Okay. R S is the seat resistance and R A, R B are the two characteristics resistance. Okay. R A and R B, you can write down, R A and R B are two characteristics resistances associated with the corresponding terminals you see that this is the RA and RB. RA means, what is RA? RA means you see that you see 1, 2, 3, 4 are the metallic ohmic contacts 1, 2, 3, 4. RA is voltage you have to measure between terminal 4 and 3. So, you have connected the voltmeter between terminal 4 and 3, and you have to measure the current between terminal 1 and 2. That means, you send current between terminal 1 and 2 and measure the voltage between terminal 3 and 4. Then if you take the ratio of the voltage to current, you will get RA, the characteristics resistance between these two terminals. Similarly, for RB, you see that you send the current between terminal 1 and between terminal 2 and 3, okay, between terminal 2 and 3, and you measure the current between terminal 1 and 4. So, that means there are two configurations. One is the adjacent configuration. You see that here 1 and 2 are the, and here it is 1 and 4, the voltage is measured. Earlier it was measured between 3 and 4. So, RA or RB can be calculated using these two values. That means, RA equals to V43 by I12 and RB equals to V14 by I23. If you consider that this is 1, this is 2, this is 3 and this is 4. Then generally the situation is very simple. Apply current I21, measure voltage V34, reverse the polarity now current is I12 and the corresponding voltage is V43. Okay. What we have done, you see that first apply current between 2 and 1, measure voltage between 3 and 4, then you reverse the polarity of the current. So, now the current will be between 1 and 2, earlier it was between 2 and 1, now it will be between 1 and 2 and the voltage will be between 4 and 3. So, all the time you have to take the data for the forward as well as the reverse polarity. We should not use the forward because configuration 1 and configuration 2 just change the direction of the current. Why we want to change the direction of the current? It is very much important to minimize the error in the measurements and also the contact resistances, the thermoelectric effect, etc. To minimize those effects, you can change the direction of the current to measure the current and voltage. And in the next class, I shall show you how from this measurement of current and voltage lead to the determination of the electrical resistivity in case of a thin sheet of materials using Van der Pau configuration. Okay. So, basically you find that one hazard is there that you have to make the ohmic contact, and ohmic contact is not very easy thing to make. First we have to choose the proper metal. Suppose aluminum in silicon is ohmic, but aluminum in gallium arsenide is non-ohmic, right. So, a very high purity material is required, otherwise there will be oxides. So, if there is an oxide in between your semiconductor and metal, then what will happen? Current will not pass, because oxide is an insulator, right. So, those things we have to take care, and then you have to annihilate. Annihilate means first you make the ohmic contact and put your sample in a furnace in argon atmosphere or nitrogen atmosphere to annihilate. Annihilate means to prevent further oxidation and also the adhesion between the semiconductor interface and the metal will be good. That means, some metal will diffuse through the semiconductor to make it very good contact. And very important consideration is that if you want to make good contact, try to make the top level highly doped. That means, if you want to make a contact on silicon, so you grow silicon, then make a very thin layer of silicon having highly doped, then you make the ohmic contact. Why? Because the highly doped area is almost similar to the metal. So, that means, there will be a metal type of interface instead of semiconductor metal type of interface. So, these are the tricks that one can play around for making the very good ohmic contact. Okay. Thank you. Let us take a break and then we shall again start.